Hi, I'm Jimmy from Princeton. In this video, I'll be presenting TidyBot, personalized robot assistants with large language models. This is joint work with collaborators from Princeton, Stanford, Nueva, Google, and Columbia. In this work, we study the task of personalized household cleanup. What we want is for a robot to pick up everything off the floor and put things back where they belong according to user preferences. One of the key challenges here is that people can have very different preferences. For example, I might want shirts to go on the shelf, whereas my friend might want them in the drawer. And so the main question we look at is, how can household robots learn your preferences from just a few examples? Our solution is to use summarization with large language models. So how does it work? We first collect the preferences of a particular person by asking for a few examples of where different items should go. For example, one might specify that jackets and jeans go on the sofa, candy bars and chips go in the plastic bin, and so on. Next, we want to generalize these examples so that the robot can handle novel objects that were not part of the examples. So instead of jackets and jeans, we might say that clothing goes on the sofa, and similarly that snacks go in the plastic bin, and so on. To do this, we leverage the summarization capabilities of large language models. We give example preferences in the form of text to a large language model, and then ask it to summarize the examples into general rules. These generalized preferences can then be used for novel unseen objects. Here's a concrete example of how this approach works with GPT-3. For the summarization step, we give 4 example placements to the language model, specifying that shirts and socks go into either the drawer or the closet. The language model will then output a summary that reflects the preferences expressed in these examples. We can then give the summary back to the language model, along with a set of novel unseen objects. The language model will then output where each unseen object should go. To evaluate our approach, we built a text-based benchmark with 96 different scenarios and 4 room types. Each scenario has a set of receptacles and a list of example placements expressing the preferences of a particular user. For evaluation, each scenario also has a list of unseen objects different from the examples. We evaluate whether our method is able to place these unseen objects into their correct receptacles. Using this benchmark, we compare with several baseline approaches and find that our summarization approach performs the best, achieving 91.2% accuracy. We also evaluate our approach on a real mobile robot, which is a holonomic mobile base with a Canova arm mounted on top. The robot is equipped with 3 high-level primitives: pick, place, and toss. We combine these primitives with 2 pre-trained visual language models to deploy our approach. First, we give an overhead image to Vile to find the closest object, which the robot will move towards. Once the robot reaches the object, it will get a close-up image, which is given to Clip to identify what the object is. The object category is used by our language model summarization approach to determine where to put the object and also how to manipulate it. The robot will then execute the selected primitive. We evaluate our overall system, which we call TidyBot, across 8 diverse test scenarios and find that it can put away 85% of objects. The test scenarios include a wide variety of real-world objects and receptacles. Here's a qualitative video of a full cleanup episode, annotated with predictions from our system. The predicted category is based on the close-up image of the object that was just picked up and comes from Clip. The predicted receptacle and primitive are based on what the predicted category is, and they both come from the large language model. For further details, please visit our project page.